The sky above you holds a secret history of violence and creation. Cosmic events have repeatedly rewritten the very story of life on our planet. By the end of this journey, you will understand the 21 specific moments when the universe reached down and reshaped our world forever. We will uncover how a single collision gave us our moon and set the stage for all life, and we will reveal the controversial evidence for a cosmic calamity that nearly erased early humanity. What do you believe is our greatest vulnerability from the cosmos today? Our planet's story begins not with a gentle whisper, but with a shattering roar. In its earliest days, Earth was a seething ball of molten rock, a world without form or future. Then came Theia, a wandering planet the size of Mars, on an inescapable collision course. The impact was not a simple merging. It was an act of cosmic violence so immense it vaporized a vast portion of our young world's mantle and splashed it out into the void. The debris from this apocalyptic encounter did not simply vanish. Instead, it was caught in a graceful orbital dance, a ring of incandescent rock that, over millions of years, coalesced into the serene, luminous moon we see today. This was far more than the birth of a satellite. It was the creation of Earth's guardian. The moon's gravitational pull acts as a steadying hand on our planet's spin, stabilizing the tilt of our axis. Without that constant presence, our world would wobble chaotically, plunging us into wildly unpredictable and extreme seasons that would make the slow, patient evolution of complex life nearly impossible. This single event gave us the rhythmic push and pull of the tides, stirring the primordial soups of our oceans, and perhaps even helping to cradle the very first sparks of life. The proof of this violent origin is written in the rocks themselves. Samples brought back from the lunar surface share an almost identical chemical fingerprint with those from Earth's mantle, a silent, scientific testament to our shared cataclysmic birth. Our gentle moon is a permanent reminder that from utter destruction can come the perfect conditions for life. Yet this was merely the universe's first foundational act, setting a stage that would soon face an even greater threat from the dark. The stability granted by our new moon was soon put to the ultimate test. A celestial storm of unimaginable fury was unleashed upon the inner solar system. For hundreds of millions of years, a relentless barrage of asteroids and comets hammered our young world in an event known as the Late Heavy Bombardment. The giant planets, shifting in their orbits, acted like gravitational pinballs, hurling countless frozen and rocky bodies inward. Earth's surface became a hellscape of continuous impacts, each one releasing more energy than all our nuclear arsenals combined. The planet was sterilized over and over again. Its ocean's flash boiled into steam and its crust melted into a global sea of lava. It was a period of seemingly endless destruction, a fiery purge that should have rendered our world permanently barren. Yet within this chaos lay a profound paradox. These same devastating projectiles were also cosmic couriers, delivering precious cargo from the frozen outer reaches of the solar system. They carried water, vast quantities of it, which eventually recondensed to fill our oceans. More importantly, they were rich with complex organic compounds, the amino acids and other molecules that are the fundamental building blocks of all living things. This presents a fascinating puzzle. Could life have ever begun without this violent delivery? The very impacts that erased life's earliest attempts also provided the raw materials for its eventual triumphant start. The evidence for this chaotic chapter is written across the face of our moon. Its ancient, cratered highlands are a preserved museum of this violent epoch. the scars remaining untouched for billions of years because the moon has no weather, no geology to erase them. Every crater we see is a silent monument to an impact that also struck Earth, a reminder of a time when our planet was forged in fire and ice. This period of cosmic artillery tested the resilience of our world's very crust, and in the end, it seeded the barren rock with the essential ingredients for life. The universe, it seems, has a strange way of creating through destruction, but the cosmos was not finished with its sculpting. An even more precise and mysterious delivery was yet to arrive, one that would tip the scales decisively in life's favor. While asteroids reshaped our world from the outside, a quieter, more profound revolution was brewing from within. The first cyanobacteria, tiny specks of life in the ancient oceans, began to perform a kind of magic. They learned to capture the energy of our sun, using it to power their own growth, and in the process they released a strange, new gas as waste. That gas was oxygen, and for the rest of the planet's primitive life, it was a deadly poison. This was the beginning of the Great Oxidation event, a slow, silent transformation that took place over billions of years. The atmosphere, once a thick, orange haze of methane and carbon dioxide, was gradually cleansed and filled with this reactive new element. This biological innovation triggered the first mass extinction on Earth, as the rising oxygen levels suffocated the vast empires of anaerobic microbes that had dominated the planet. Yet from this ecological catastrophe, a new world was born. The oxygen did not just linger in the air. High above the surface, it reacted under the sun's intense light, weaving a delicate, invisible shield. This was the ozone layer, a protective blanket that for the first time filtered out the sun's most harmful ultraviolet radiation. With this shield in place, life could finally dare to leave the safety of the water and colonize the barren continents. Every breath we take is a legacy of that ancient microbial revolution. It shows us that life is not just a passenger on this planet, but a powerful geological force, capable of altering the very air and sky. The energy for this entire transformation came from a single, distant cosmic source, our sun, proving that the influence of the cosmos on life is not always a violent impact, but sometimes a gentle, life-giving light. The world you know vanished beneath a sheet of white that stretched from pole to pole. This was Snowball Earth, a planet locked in a deep freeze so profound that even the equator was covered in ice, possibly over a mile thick. For millions of years, Earth resembled a perfect frozen marble drifting in space. The stage was set by a fainter young sun, but the real culprit was a runaway chill. As ice spread, its brilliant white surface reflected more of the sun's precious warmth back into space, which in turn cooled the planet further and created more ice. This is the ice albedo feedback loop, a self-reinforcing cycle that plunged the entire globe into an icy grave. Life was pushed to the brink, surviving only in isolated pockets of relative warmth, perhaps around volcanic vents or in tiny pools of meltwater under the ice. How does a planet ever escape such a perfect global winter? The rescue came from deep within the Earth itself. Volcanoes, undeterred by the frozen surface, continued to pump carbon dioxide into the atmosphere. With no liquid water or plant life to absorb it, this powerful greenhouse gas built up for eons, slowly thickening the atmospheric blanket until finally, it trapped enough heat to trigger a catastrophic melt. The thaw was as extreme as the freeze. Earth swung from an icehouse into a searing greenhouse, with temperatures skyrocketing and rains of incredible acidity washing the newly exposed continents. This violent climatic whiplash may seem like a disaster, but it created a strange opportunity. The oceans, now rich with minerals scoured from the land by the Great Melt, became a nutrient soup, potentially fueling a rapid explosion of new life forms. Some scientists even suggest these extreme cycles of freeze and fire, possibly influenced by subtle changes in Earth's orbit over hundreds of millions of years, acted as a brutal evolutionary crucible. Life was forced to adapt or die, and in that struggle, the first complex organisms may have found their footing. The resilience forged in this global ice age was a vital test, preparing life for the next, more sudden blows that would arrive from the heavens themselves. Even as life was recovering from the global freeze, a new threat emerged from the asteroid belt. A colossal parent asteroid, perhaps hundreds of miles across, suffered a catastrophic collision, shattering into countless fragments. This debris was flung into new orbits, creating a prolonged meteorite shower that bombarded the inner solar system for millions of years. Earth, moving through this cloud of cosmic shrapnel, experienced a significant spike in its impact rate. This was not a single, world-ending cataclysm, but a persistent rain of fire. Individual impacts would have been locally devastating, each one a regional apocalypse of fire and shockwaves that scorched landscapes and churned the coastal shells where most complex life thrived. Imagine the environmental stress of this era. An ecosystem recovering from an ice age would now face repeated, unpredictable blows from the sky, a constant pressure that could have pushed some species to their limits. The evidence for this ancient bombardment is not just in craters, but in the very sediments laid down at that time. Scientists drilling into Ordovician rock layers have found a sudden, dramatic spike in a rare isotope called helium-3. This helium-3 is not from Earth. It is a direct tracer of cosmic dust, the fine powder that would have drifted down from that long-vanished asteroid breakup. It is the silent, chemical fingerprint of a solar system in turmoil. This event teaches us a crucial lesson about cosmic threats. We often focus on the single, dinosaur-killing-sized impactors, but history shows that a prolonged period of smaller, frequent impacts can be just as disruptive. It creates a background level of chaos, a steady drumbeat of change that alters ecosystems and shapes the destiny of life. This constant cosmic pressure sets the stage for the moments when that drumbeat becomes a single, deafening roar, leading us directly to the most famous extinction event of all time. The quiet rhythm of recovery was shattered once more. During the late Devonian period, life in the oceans suffered a series of brutal, mysterious blows. This was not one single extinction, but a drawn-out agony of pulsed events that, over millions of years, devastated the planet's warm, shallow seas. Reef systems that had thrived for ages crumbled into ghost towns of calcium carbonate. The great armored fish, the placoderms, which had ruled as the ocean's titans, were systematically wiped out. For a long time, scientists puzzled over what could cause such a slow, grinding collapse. The answer may have come from the sky, not once but several times. Scattered across Devonian rock layers around the world are telltale signs of cosmic violence. Geologists have discovered thin, dark bands rich in the element iridium, a metal that is rare on Earth's surface but common in asteroids. In those same layers, they find shocked quartz, crystals whose internal structure has been fractured by pressures so immense they can only be generated by the force of a massive impact. These are the undeniable fingerprints of asteroids striking the planet. Yet the impacts themselves were only the trigger. Each collision would have kicked up vast clouds of dust and vaporized rock, blotting out the sun and plunging the world into a prolonged winter. This global chill could have then set off a chain reaction of disasters on the ground, triggering colossal volcanic eruptions that further poisoned the atmosphere. The real killer, however, was in the oceans. As temperatures swung wildly and nutrients from the scarred land washed into the seas, they triggered massive algal blooms. When these blooms died and sank, their decomposition sucked all the oxygen from the water, creating vast dead zones where nothing could breathe. Marine life was caught in a perfect storm, trapped between a darkened sky and suffocating depths. The world that emerged from this prolonged crisis was forever changed. The downfall of the dominant trilobites and armored giants cleared the ecological stage. Into this void swam new, more agile predators. Early sharks honed their sleek forms, and the first bony fish began to diversify, their lightweight skeletons and advanced swim bladders giving them a critical advantage in the struggling seas. This moment in Earth's history is a powerful lesson in interconnected chaos. A cosmic impact is bad enough, but when it resonates with the planet's own volatile geology, the combined effect can amplify into a catastrophe that reshapes the very future of life. The stage was now set for a new cast of characters to leave the water and conquer the land. 250 million years ago, the world almost ended. This was the Permian-Triassic extinction, an event so catastrophic it earned the name the Great Dying. In the blink of a geological eye, over 90% of all marine life and 70% of land animals vanished forever. The fossil record does not show a slow decline. It shows a sudden, brutal wall of death. For decades, the prime suspect has been a colossal volcanic nightmare in what is now Siberia. The Siberian traps did not erupt in a single explosion, but in a prolonged, continent-scale fury that poured enough lava to cover the entire United States in molten rock a mile deep. These volcanoes did more than just bury the land. They baked the bedrock, releasing trillions of tons of carbon dioxide and methane, superheating the entire planet. The oceans turned acidic and suffocating, becoming vast, lifeless soups of poison. But what could have triggered such a sustained and violent outburst from Earth's own interior? A controversial clue emerged from deep within the rock layers of that time. Scientists discovered strange, cage-like molecules called fullerenes, and trapped inside them were gases with a chemical signature that did not match our planet. These were extraterrestrial gases hinting at a cosmic visitor. The theory is as terrifying as it is simple. A large asteroid impact striking at just the right place and time could have sent a shockwave through the planet's crust, fracturing it like an eggshell and unleashing the volcanic fury that was waiting below. The Earth's own destructive power and a random cosmic blow may have joined forces in a perfect storm of annihilation. The world that emerged from this hellscape was a ghost world, empty and quiet for millions of years. But in that emptiness lay an opportunity. The few small, hardy survivors, our own mammalian ancestors among them, inherited a nearly blank slate. They diversified and evolved in the vacant landscapes, setting the stage for the rise of new giants. The Great Dying stands as the ultimate warning. It shows us that the greatest threat may not come from the sky or from the ground alone, but from a devastating collaboration between the two. Yet, even after this, the cosmos was not finished with its targeted strikes. The next one would be so precise it would topple the rulers of the world and clear a path for an entirely new kind of animal. The reign of the dinosaurs almost never happened. For millions of years after the Great Dying, life on land was a world of smaller, tentative creatures, a slow recovery dominated by large, crocodile-like amphibians and a variety of other reptile groups. Then, around 200 million years ago, another great filter arrived, the Triassic-Jurassic extinction. This event did not have the sheer body count of the Permian catastrophe, but its effects were just as profound for the future of our planet. It systematically removed the dominant land animals of the time, those large amphibians and many early reptile lineages, emptying the ecological throne room. Into that vacant space stepped a group that had been living in the shadows, the dinosaurs. The primary engine of this change was a geological upheaval of epic proportions. The supercontinent Pangaea, which had wrapped all the world's landmasses into one giant entity, began to tear itself apart. This rifting was not a gentle separation. It was a planetary-scale wound, unleashing floods of lava across what would become the Atlantic Ocean, a region known as the Central Atlantic Magmatic Province. For hundreds of thousands of years, volcanoes poured forth basalt and pumped the atmosphere full of carbon dioxide, triggering intense global warming and turning the oceans acidic. The world was once again under immense volcanic stress, but geology may not have acted alone. Hidden in the Canadian wilderness lies the Manicouagan crater, a 70-kilometer-wide scar dated almost perfectly to this extinction event. This is the mark of an asteroid several miles in diameter. The impact's immediate effects would have been horrific, but its true power was as an amplifier. It took a planet already reeling from volcanic chaos and delivered the final, decisive blow. The soot from fires and the dust from the impact would have deepened and prolonged the volcanic winter, while the added greenhouse gases from vaporized rock could have supercharged the existing warming trend. Species already clinging to survival found their world tipping past a point of no return. This event reveals a chilling and recurring pattern in Earth's history. A cosmic impact is rarely just a singular disaster. More often, it is the coup de grace, the final straw that breaks the back of an ecosystem already under severe strain. The downfall of the old giants was the ultimate opportunity for the dinosaurs. With their competitors gone, they exploded in size and diversity, seizing control of every continent and beginning their own magnificent and ultimately doomed rule over the planet. 66 million years ago, a mountain of rock and iron fell from the sky. This was not just another impact, it was the impact, the one that defines all others. The Chicxulub asteroid, a 10-kilometer-wide behemoth, did not simply strike the Yucatan Peninsula, it effectively struck the entire planet at once. The energy released was beyond human comprehension, billions of times more powerful than the atomic weapon that leveled Hiroshima. For any creature living that day, the world ended in stages. First came the flash of heat, a global firestorm that ignited continents. Then came the earthquakes shaking the very foundations of the planet. Then came the waves, mega tsunamis hundreds of meters high that scoured coastlines thousands of miles away. But these were only the opening acts of the apocalypse. The real killer was what the impact threw into the sky. Vaporized rock and sulfur aerosols formed a thick, black shroud around the entire Earth, blocking the sun's light for years, perhaps even decades. This was the impact winter. Photosynthesis ground to a halt, plants withered and died, the great herbivores that depended on them starved, and the terrifying carnivores that hunted them soon followed. The reign of the dinosaurs, a magnificent dynasty that had lasted for over 180 million years, was over in a geological instant. In the silent, shadowy world that remained, the inheritors were already scurrying in the undergrowth. Small, furry, warm-blooded mammals which had lived for eons in the shadows of the giants now found the world empty of their most dominant predators. With abundant food and space, they diversified at an astonishing rate, evolving into every form of life we see around us today, including, ultimately, us. This event is the ultimate example of cosmic randomness, a single rock from the asteroid belt rewriting the entire future of a planet. It stands in stark contrast to the next great cosmic influence, one that operates not with sudden violence, but with a slow, rhythmic, and predictable pulse that has guided life for millions of years. The dinosaurs were gone, but the cosmos had not yet finished its work on our planet. 34 million years ago, the world was still a warm, humid greenhouse, a place where palm trees grew on the shores of the Arctic Ocean. Then, with surprising speed, the planet plunged into a deep chill. This was the Eocene-Oligocene extinction, a pivotal moment that slammed the door on the ancient greenhouse world and ushered in the icehouse planet we know today. The change was driven by the slow, inexorable dance of the continents. Australia pulled away from Antarctica, and the deep channel of the Drake Passage opened between South America and the frozen southern continent. For the first time, a continuous, frigid current began to circle Antarctica unimpeded, isolating it from warmer tropical waters. This Antarctic circumpolar current acted like a refrigerating loop, steadily drawing heat away from the continent and allowing a permanent ice sheet to form for the very first time. But geology may not have acted alone. At this precise moment in the fossil record, a mountain of rock and ice slammed into what is now Siberia, carving out the colossal Popigai crater, one of the largest impact scars on Earth. The collision would have thrown vast quantities of dust high into the stratosphere, reflecting sunlight back into space and causing a sharp, sudden global cooling. This cosmic kick may have been the final push, tipping a climate already on the brink into a new, frozen state. The effects on life were profound. In the oceans, the cooling waters caused a major extinction among tiny, surface-dwelling organisms called foraminifera, whose fossil shells paint a clear picture of the temperature crash. On land, the dense, humid forests that had covered much of the globe began to retreat, replaced by open grasslands. This shift in habitat spelled doom for many of the archaic mammal groups that had thrived in the lush forests, creatures with strange, specialized teeth and diets. In their place emerged new, more adaptable animals, including the first recognizable members of the dog and cat families, ancestors built for speed and endurance in the expanding open country. This event reveals a subtle but powerful cosmic truth. An asteroid impact is not always just a single, catastrophic day of fire. Sometimes it is the flick of a domino that starts a chain reaction lasting for epochs. Popigai impact did not just cause a temporary winter, it helped lock the world into a new climatic regime, one of polar ice and seasonal extremes that would dominate for millions of years, setting the stage for the world we inhabit today. And as the planet continued to cool under this new icy order, another, more rhythmic cosmic clock began to dictate the very pulse of life itself. A slow, celestial chill began to descend upon the world. Starting around 15 million years ago, the warm, moist climate of the Miocene epoch gave way to a cooler, drier reality. This was not a sudden impact winter, but a gradual transition spanning millions of years, a creeping change with a cosmic dimension. The primary drivers were earthly, the colossal uplift of mountain ranges like the Himalayas and the Andes, which rerouted winds and reshaped entire continents. Yet scientists have proposed a fascinating, additional influence from deep space. As our solar system journeyed through a particular spiral arm of the Milky Way, it may have passed through a region with a stronger interstellar magnetic field. This magnetic shield could have deflected some of the cosmic rays that normally bombard our atmosphere. Why would that matter? Because cosmic rays are thought to seed the formation of clouds. Fewer cosmic rays could have meant fewer clouds, and with less cloud cover, more of the sun's heat might have radiated back into space, subtly contributing to the planet's long-term cooling trend. It is a profound idea that our position in the galaxy itself could be a hidden hand on Earth's thermostat. The consequences for life were revolutionary. Lush global forests shrank, replaced by vast, open savannas. This was a catastrophe for the creatures built for a world of dense woodlands. The evidence is written in the bones of ancient horses. Early horses like Hippohippus were small, leaf-eating browsers with 3 toes for navigating soft forest floors. As the forests retreated, they vanished. But from their lineage emerged a new kind of horse, one adapted for the emerging grasslands. Animals like Merychippus evolved high-crowned teeth to withstand the gritty silica in grass, and their legs lengthened, their middle toes strengthening into a single, hard hoof perfect for sprinting across open plains to escape new, faster predators. This faunal turnover was a complete restructuring of life on land, a shift from browsers to grazers, from hidden ambush to open pursuit. This moment reveals a deep and subtle connection. The slow drift of our solar system through the galaxy, an event on a scale of hundreds of light years, may have helped create the open landscapes that forced the evolution of swift, alert mammals. It was on these new, expanding grasslands that a family of primates would eventually descend from the trees, stand upright, and begin their own extraordinary journey. The stage was almost set for humanity, but first, the cosmos would deliver one more series of violent reminders, this time within living memory. 74,000 years ago, a terrestrial titan roared. Mount Toba in Indonesia did not simply erupt, it disintegrated in the single most explosive volcanic event in 2 million years. It unleashed a force thousands of times greater than any eruption in recorded history, vomiting nearly 3,000 cubic kilometers of rock and ash into the sky. The immediate devastation was regional, but the true cataclysm unfolded in the atmosphere. Sulfur aerosols from the blast formed a global shroud, reflecting sunlight back into space and plunging the planet into a volcanic winter that may have lasted for a decade. Temperatures plummeted worldwide and acid rain fell upon a dying landscape. For our ancestors, Homo sapiens, this was a moment of supreme crisis. The world they knew was vanishing under a cold, gray sky, with plant life withering and the great herds they depended on disappearing. Genetic studies of modern human populations point to a startling fact. Right around this time, our species went through a severe population bottleneck. The entire human race may have been reduced to just a few thousand individuals, perhaps only 1 to 10,000 breeding pairs, clinging to survival in isolated refuges. We were pushed to the very brink of extinction. This terrestrial event is a vital part of our cosmic story because it perfectly mirrors the impact winter that followed the asteroid that killed the dinosaurs. The source of the calamity was different, but the climatic effect was the same, a prolonged, sunless winter that tests life to its absolute limits. The survival of our species through this decade-long winter was not guaranteed. It may have been our greatest evolutionary test. Some theorists propose that this extreme pressure selected for the most critical human traits: enhanced cooperation, complex communication, and advanced planning. Only the smartest, most socially adaptable groups, those who could share scarce resources and care for their young through years of famine, would have endured. In this sense, the ashes of Toba may have forged the very foundations of modern human society. This near annihilation shows that the threat of a cosmic winter is not just an abstract theory from the distant past. It is a danger that our own species has faced in its recent history, a ghost of a catastrophe that almost was. It underscores a humbling truth: intelligent life is a fragile flame, easily snuffed out by planetary upheaval, whether its origin is from the ground below or the sky above. The ground beneath the feet of early North Americans suddenly turned to fire. A controversial but compelling theory suggests that 12,800 years ago, a fragmented comet streaked across the sky and exploded in a series of devastating airbursts over the continent. The force was unimaginable, a rain of fire from the heavens that scorched the Earth and ignited a firestorm that consumed nearly 10% of the planet's biomass. The evidence for this cosmic strike is written in a thin, dark layer of sediment, that marks a stark before and after in the geological record. Within this black mat, scientists have found a strange and otherworldly collection of materials, a layer of soot from continent-spanning wildfires, microscopic nanodiamonds formed under immense pressure and heat, and a surprising spike in the rare metal platinum, an element common in asteroids but rare on Earth's crust. This was the trigger for the younger Dryas, a sudden and violent reversal of the climate. Just as the world was finally emerging from the last ice age, enjoying a warm and stable period, this event plunged the planet back into a deep freeze that lasted for 1,300 years. The consequences for life were immediate and brutal. In North America, the magnificent megafauna that had thrived for millennia, the woolly mammoths, the giant ground sloths, and the saber-toothed cats, were suddenly pushed over the edge into extinction. They could not survive the rapid return to glacial conditions and the loss of their habitats to the fires and the cold. This climatic shockwave also shattered human societies. The sophisticated Clovis culture, known for their distinctive spear points used to hunt these giant creatures, vanished from the archaeological record almost overnight. Their entire way of life, built around tracking and hunting the great herds, collapsed when those herds disappeared. This hypothesis, while still debated, forces us to reconsider the timeline of human progress. It suggests that a cosmic event, not so different from the one that wiped out the dinosaurs, occurred at the very dawn of our own history, disrupting our development at a critical juncture. The debate itself is a powerful reminder that the story of our planet is not fully written, and that every new layer of Earth we examine might hold a clue to another forgotten catastrophe from the stars. The silence of the Siberian taiga was shattered in an instant. On a June morning in 1908, a fireball brighter than the sun ripped across the sky above the Tunguska River. It ended not with an impact crater but with a cataclysm in mid-air. A stony asteroid or fragment of a comet, roughly the size of a 20-story building, exploded several miles above the ground. The blast released energy comparable to a large hydrogen bomb, flattening 80 million trees across 2,000 square kilometers of remote forest. The shockwave circled the globe twice, and for nights afterward, the skies over Europe and Asia glowed so brightly that people could read newspapers outdoors at midnight. The sheer force of the airburst was so immense that it left no traditional crater, instead leaving a radial scar of devastation, every tree pointing away from a silent, empty epicenter. For years, the remoteness of the location kept the full scale of the event a mystery. When the first scientific expedition finally reached the site nearly 20 years later, they found a landscape of unimaginable ruin, a forest laid to waste by a punch from the sky. The Tunguska event was a direct hit, but a lucky one. Had the asteroid's trajectory been different, had it arrived just a few hours later in its rotation, it could have exploded over a major European city, vaporizing millions in a flash. This was not an extinction-level event from the deep past. It was a precise and terrifying warning shot. For the first time in recorded history, humanity was forced to collectively recognize that the empty space above our heads is not so empty after all. This single event in a remote forest fundamentally shifted our perspective, transforming cosmic impacts from a geological curiosity discussed in textbooks into a clear and present danger that required a response. The global scientific interest that followed Tunguska planted the seeds for everything that came next, from tracking near-Earth objects to the creation of dedicated planetary defense programs. It was the moment we looked up and realized we needed to start paying attention. This wake-up call sparked a new era of vigilance. But what happens when we are not just observers, but active participants in a cosmic collision? The sky itself seemed to burn. In the first days of September 1859, a celestial firestorm erupted, but its fury was not felt as heat or impact. It was an invisible wave of energy, a coronal mass ejection of unimaginable scale that had traveled from the Sun and slammed into Earth's magnetic shield. The result was the Carrington event, a geomagnetic storm so powerful it turned night into day across the globe. People in Havana and Jamaica stood in awe as curtains of crimson and emerald light, the aurora borealis, danced in tropical skies where they had never been seen before. But this beautiful display was merely the visible symptom of a planetary-scale electrical surge. Beneath these shimmering lights, the world's most advanced technology, the telegraph network, went utterly mad. Operators were thrown from their stations as sparks erupted from the equipment, and telegraph papers spontaneously burst into flames from the induced currents coursing through the wires. In some cases, the power was so great that operators found they could disconnect their machines from the batteries and still send messages, powered solely by the electricity in the air, the very sky itself acting as a generator. This was not a localized blackout, it was a worldwide short circuit, a preview of a new kind of cosmic threat. The Carrington event revealed a profound and unsettling truth. Our life-giving sun is also a capricious star, capable of launching solar hurricanes that can bypass our atmosphere and attack the central nervous system of our civilization, our power grids and electronic networks. A storm of that magnitude striking our world today would not just burn a few telegraph papers, it would induce catastrophic currents in our continent spanning high-voltage power lines, frying transformers and plunging entire nations into a blackout that could last for months or even years. It would silently disable the satellites we rely on for navigation, communication, and finance, creating a cascade of failures that would halt global commerce and cripple modern life. This moment permanently altered our understanding of our relationship with the sun, transforming it from a distant benefactor into a source of volatile space weather. Our vulnerability is not static, it grows with every new power line we string and every new satellite we launch, a ticking clock set by our own technological advancement. This threat from our own star is a constant, quiet reminder that the cosmos can disrupt our world without a single rock ever striking the ground. While the sky delivered its violent blows, a quieter, more patient force was reshaping the world from below. During the Cretaceous period, the planet was almost unrecognizable. Vast, warm, shallow seas spilled over the continents, dividing North America into two island masses and transforming much of Europe into a sprawling archipelago. These were not oceans as we know them, but immense inland waterways, sometimes hundreds of miles wide yet only a few hundred feet deep. This was a world dominated by water, a global experiment in marine geography. Primary engine for this great flood was the relentless churn of plate tectonics. As the seafloor spread rapidly at mid-ocean ridges, the younger, hotter, and therefore more buoyant rock pushed the existing ocean basins upward, effectively displacing seawater onto the continents. But layered over this grand geological process was a subtle celestial rhythm. The gravitational pull of Jupiter and Saturn, the solar system's giants, gently tugs on our planet, causing slow, predictable variations in Earth's orbit and axial tilt. These are the Milankovitch cycles, and while they are too weak to create the seas themselves, they acted as a precise climatic dial. As these cycles minutely altered the amount and distribution of sunlight reaching Earth, they caused the polar ice caps, which were already minimal, to wax and wane. This, in turn, modulated the sea levels by dozens of meters, causing the great inland seas to pulse and retreat across the continents over hundreds of thousands of years. Can you envision a world where the heartland of America is a tropical seaway, patrolled not by bison but by monstrous marine reptiles? These shallow, sun-drenched waters became a cradle of evolution for life like the mosasaurs, giant marine lizards that became the apex predators of their age, and the long-necked plesiosaurs that glided through the warm currents. The sheer abundance of life in these fertile seas laid down the skeletons that would become the great oil fields we depend on today. Then, as the orbital cycles shifted and the seafloor began to cool and sink, the waters slowly drained away. This great regression of the seas was as transformative as their arrival. Land bridges emerged, connecting continents and allowing dinosaurs and early mammals to migrate and mix in ways never before possible. The exposed seabeds became vast, fertile plains, new frontiers for terrestrial life to conquer. This 16th moment reveals a profound truth. The gentle, rhythmic gravitational tugs from our celestial neighbors, operating over millions of years, can dictate the very shape of our continents and the fate of its inhabitants. It is a cosmic influence not of sudden destruction, but of slow, patient sculpting, proving that the universe guides life not only with cataclysmic fists, but also with imperceptible, guiding hands. A rhythmic pulse of ice and interlude has defined our world for the last 2.6 million years. This is the Pleistocene epoch, a time of dramatic climatic swings where colossal ice sheets, sometimes over a mile thick, advanced from the poles to cover nearly a third of the planet, only to retreat again in warmer periods called interglacials. The engine for this great planetary heartbeat is not found on Earth, but in the precise clockwork motion of our world through space. These are the Milankovitch cycles, 3 distinct orbital variations that act together like a complex climate control dial. Eccentricity describes the subtle shift in Earth's orbit from a near circle to a slight ellipse over a 100,000-year cycle. Axial tilt, the angle of our planet's pole, wobbles between 22 and 24.5 degrees every 41,000 years, altering the intensity of our seasons. And precession, a slow 26,000-year wobble of the axis itself, changes which hemisphere is tilted toward the sun during its closest approach. Individually, these changes are minute, but when they align to minimize summer sunlight in the northern hemisphere, snow that falls in winter does not fully melt. Over centuries, it accumulates, compacts into ice, and begins to flow, initiating an ice age. The evidence for this cosmic pacing is locked in the ice itself. Core samples drilled from ancient glaciers reveal a clear, repeating pattern of atmospheric composition and temperature, perfectly matching the rhythmic beat of these orbital cycles. For all life, this was an era of relentless pressure and forced movement. With so much water locked up in ice, sea levels could drop by over 400 feet, exposing land bridges like Beringia, which connected Asia and North America. Creatures were constantly on the move, tracking their shifting habitats or evolving new adaptations to survive the cold. The woolly mammoth grew its thick coat and huge, curved tusks, while the cave lion developed a stockier build. And it was on this unstable, challenging stage that our own species, Homo sapiens, completed its evolution and began its great global migration. We did not evolve in a stable, tranquil world, but in a crucible of climatic chaos, our intelligence and social flexibility forged by the need to cope with an environment that was constantly in flux. The very rhythm of the ice ages, driven by the slow dance of our planet, may have been the essential pressure that sculpted the resilient, adaptable mind that now seeks to understand its own cosmic origins. How different would our story be if Earth's orbit were a perfect circle, its axis forever steady? This cosmic clock has not stopped ticking, and its next turn is already written in the stars, a future chapter in our planet's ongoing dialogue with the heavens. Humanity has now become a geological force in its own right. Scientists propose we have entered a new epoch called the Anthropocene, An age defined by the profound and permanent changes our species has etched into the very rock and atmosphere of the planet. Yet woven into this era of human dominance is another, equally monumental shift, our awakening to the cosmos. For the first time in 4 billion years of life on Earth, a species is consciously looking upward, not in passive wonder but in active vigilance. We have begun to catalogue the asteroids that cross our path, to monitor the sun for violent flares, and to design technologies meant to shield our world. This is not just another cosmic event, it is a meta-cosmic event, a fundamental change in the relationship between life and the universe. We are transitioning from being potential victims of a random impact to becoming active agents in our own planetary destiny. Consider the double asteroid redirection test. A spacecraft intentionally crashed into a small moonlet to alter its orbit. This was not science fiction. It was a live experiment in planetary defense, a practice run for the day we might need to gently nudge a threatening object away from a collision course with Earth. This conscious effort to prevent a future cosmic cataclysm marks a rupture in the historical pattern. Every other moment on our list was a blindside, a brutal act of nature that life had to endure or perish from. Now we see the punches coming. Our global network of telescopes is like a planetary immune system, constantly scanning the darkness for incoming threats. This awareness itself is a form of cosmic evolution, where intelligence becomes a survival trait on a planetary scale. The story is no longer just about what the universe does to us, but about what we, as a conscious part of that universe, choose to do in response. This newfound power brings with it a profound responsibility, not just to our own future, but to the entire continuity of life on Earth that we now have the potential to safeguard. A world away, a planet saved our own. In July 1994, the gaze of every major telescope on Earth and in space was fixed on Jupiter. Humanity became a collective witness as 21 fragments of a comet named Shoemaker-Levy 9, which had been torn apart by the giant planet's gravity 2 years earlier, began a 6-day-long procession of fire. One by one, they plunged into Jupiter's southern hemisphere at speeds over 200,000 kilometers per hour. Each impact released an explosion of energy greater than the world's entire nuclear arsenal, creating superheated plumes of gas that rose thousands of kilometers above the cloud tops. When the violence subsided, Jupiter was left with a chain of black scars in its atmosphere, each one a dark bruise larger than our entire planet. These were not abstract calculations or theoretical models. This was a live broadcast of cosmic destruction on a scale we had only ever imagined. For the first time, we saw the fate that befell the dinosaurs playing out in real time on another world. The stark, undeniable lesson was that our solar system is not a quiet, orderly place. It is a dynamic and sometimes violent system where such collisions are not relics of the deep past but ongoing events. We realized that Earth exists in the same cosmic neighborhood, a potential target in a celestial shooting gallery where Jupiter often acts as a gravitational shield, but where a stray bullet can always get through. The public and political response was immediate and profound. The visual proof of those Earth-sized scars transformed planetary defense from a niche scientific concern into a global priority. Funding for near-Earth object surveys skyrocketed. New programs were launched with the explicit goal of finding and tracking every potentially hazardous asteroid large enough to threaten our civilization. The Shoemaker-Levy 9 impact did not change Earth's physical environment, but it forever changed our perception of it. It gave us a sobering, front-row seat to our own potential future and ignited a race to ensure we never share the dinosaurs' fate. This collective awakening set the stage for the next logical step, a question that would move us from passive observation to active defense. our planet is constantly bathed in an invisible rain from the depths of the galaxy. Cosmic rays, high-energy particles accelerated by distant supernova and black holes, stream through the void and pierce our protective atmosphere. When one of these microscopic bullets strikes a living cell, it can slice through the delicate strands of our DNA like a pair of molecular scissors, scrambling the genetic instructions inside. Most of the time, the cell repairs this damage, or the mutation is harmful and the cell simply dies. But on rare, pivotal occasions, the scrambled code creates a new instruction, a random change that proves to be a surprising advantage. This is the most subtle and persistent of all cosmic influences, a quiet background hum of mutation that has been ticking away for billions of years. It is not a dramatic event of fire and ice, but a silent partner in the engine of evolution itself. Without this constant, low-level cosmic radiation providing a steady trickle of genetic variation, the raw material for natural selection would be vastly diminished. Can you picture the immense timescales? Over millions of generations, this gentle cosmic rain has helped to paint the incredible diversity of life we see around us. A beetle's unique shell, a flower's specific color, the immune system that fights off a new disease, all of these could trace their ultimate origin back to a random, cosmic particle that struck an ancestor's gene and changed everything. This force connects every living thing to the violent heart of the galaxy, reminding us that we are not just living on a planet, but within a dynamic and creative cosmos. The universe does not only shape life with catastrophic fists, it also writes its signature, letter by letter, into the very code of existence. This silent, ongoing collaboration between the heavens and our biology raises a profound question about our future. The clock is still ticking on our planetary defense. While the great bombardments of the past are behind us, the solar system remains a dynamic and sometimes dangerous place, with thousands of known near-Earth asteroids still tracing paths that cross our own. These are not doomsday prophecies, but mathematical probabilities tracked by astronomers around the globe. Each one is assigned a calculated risk, a non-zero chance that its future orbit might one day intersect with ours, decades or even centuries from now. This is not a cause for panic, but the very reason for our vigilance. The successful double asteroid redirection test mission marked a profound turning point in human history. For the first time, a species on this planet intentionally reached out and nudged a celestial object, proving that we can, in principle, alter the trajectory of a potential threat. That spacecraft's kinetic impact was more than a technological triumph. It was a declaration. We are no longer content to be passive passengers on a world subject to random cosmic violence. This global effort to map the skies and develop deflection technologies represents humanity's collective will to survive, to protect the entire biological legacy of our planet. The next great cosmic moment may not be an impact but an avoidance. It could be the story of how, through international cooperation and brilliant ingenuity, we saw a threat coming and gently, deliberately pushed it aside. That would be the ultimate astonishing moment, the day we transition from a species shaped by ancient stellar events to one that actively secures its own future among the stars.